All right, so section 10.1 deals with matchings and independence in graphs. Now, we've already looked at the concept of independence as it relates to vertices. We say a set of vertices is independent if and only if there exist no edges between the vertices in the set. Now, we can also have we can also extend the concept of independence to edges. When we say that two edges are independent if they are not incident with a particular vertex, not both incident with a particular vertex. Now, if we look at the following definition, if G is a graph where M is a subset of the edge set of the graph G, then if no two edges of M share a vertex, in other words, no two edges is incident with the same vertex, then M is a matching in G. Right. So in that sketch there, if we look at the sets of edges E1 and E2, so it's basically as E1 and E4. Right, you can see clearly those two blue edges, they are not, they don't share any vertices, right? So that is clearly a matching. And then E1, E3, E5, E1, E3, and E5. That's also a matching because none of the blue edges share a vertex. Now, if a matching, or rather a matching of maximum cardinality in G is a maximum matching of G. Okay, so we look at maximizing the number of edges in my matching set to form a maximum matching. Right, now note that the set in the previous example, E2 and E4, is maximal. It is maximal with respect to the matching property. Why is that? So let's look at E2 and let's look at E2 and E4. Right, that's clearly a matching. Now, why is it maximal? It's maximal because if we add any extra edge to my set, so let's say we add that edge there, then we see that E1 and E2 both share a vertex. Okay, so it's not going to satisfy the matching property. If we add that edge again, not going to happen because then those edges share vertices, E2 and E3. If we add any one of those edges there, again we share a vertex, again with that one as well. So that's maximal. It means I cannot go and add any edges. And if I do, I sit with a violation of the matching property. If one looks at E1, E3, E5, E1, E3, and E5, that is a maximum matching. First of all, it's a matching, and I cannot go and construct another matching that has got more than 3 edges. Okay, that's the largest possible set of edges that I can get with the matching property that satisfies the matching definition. Right, so it's not possible to go beyond 3. And also E1, E3, E5 is obviously maximal. Adding any edge to it is going to yield a violation. It's pretty much going to violate the matching property. Right, now the cardinality of a maximum matching of G, That is called the matching number of G, and it's denoted by alpha prime of G. So that's the matching number of G. So you basically look at all your possible matchings that exist in your graph G, and then you choose the one with largest cardinality, and that is the that's the matching number of G. Now, as an observation, the matching number is at most half the number of vertices. Now, this should actually sort of make sense because that is pretty much the largest. That is the largest number of edges that your matching can contain. Now, if hypothetically, if we look at the graph G there, so if you pair off the vertices of your graph using a matching, so you start pairing off. You start using matching edges to pair off the vertices. I mean, it's pretty straightforward to see that if the graph is even order, then the largest possible amount of matching edges that you can reach is pretty much the cardinality of G divided by 2. And that is if the order of G is even. But also if the order of G is if G is odd order, I mean, then it will work the same as well. Again, the maximum number of matching edges that you can get in your graph is pretty much, if you were to count that, again, you cannot pair this vertex off to any other vertex because the matching property won't be satisfied. And so obviously the number of edges in this case in this maximum matching is, again, it's at most n-1/2. Okay, so it is obvious that the matching number is at most it's pretty much at most the floor of n/2. If we go back to our example there, in that little tree there, the matching number of that graph G is clearly 3. And the reason for that is one can obviously not construct a matching of cardinality greater than 3, and we therefore we have an example of a matching that has cardinality 3. So therefore we have exact equality for the matching number. Now, just as for interest's sake, a nice little application of the matching number is, say a company has got n employees labeled W1 up until Wn, and we have tasks that we have to assign these employees, call it T1 up until Tm. Now, if we let G be the bipartite graph with vertices W1 up until Wn, there's just it's just a typing error there, and edges Wi, T, J, whenever Wi is qualified for task Tj, then a matching represents an assignment of tasks to qualified employees. Right. So obviously you want to have as many qualified employees to be given the right tasks, and that involves getting the matching number. Right. Again, given a G, find a maximum matching to then answer that question. So I mean that's a little application. If we were to go deeper into the knowledge surrounding this particular parameter, we just need to quickly look at a few more definitions. So given graph G with a matching M, we say a vertex not incident with any edge in the matching, that is an M unmatched vertex, right? And if M has no unmatched vertex, then we say that M is a perfect matching. So if we look here, so let's let that be a matching there, right? So we've basically matched all the vertices. Okay, so the set of blue edges is my matching M. One can clearly see that every vertex in the graph G is incident with one of the matching with a matching edge, and therefore it is matched. It's M matched, and it's clear there that no vertex is unmatched, is M unmatched. So therefore in that particular example there, that is a perfect matching. That is a perfect matching. So obviously if a graph has odd order, then it has no perfect matching. Then the next theorem is it's more of a sort of an observation. If you've got two different matchings of G, and you look at the spanning subgraph of G, in other words, what is a spanning subgraph? It's a subgraph that's got the same number of, that's got all the vertices of G, and specifically the edge set of this spanning subgraph is going to be defined as follows. So you're going to take the matching M1, and from that you're going to remove all the edges from the second matching M2, and then all those edges you're going to take the union of that with the edges that you get from by taking the second matching, and from that you remove all the edges from the first matching. Okay, and that is a graph that has got the following properties. Each one of the components of H is either an isolated vertex, or it could possibly be an even cycle whose edges alternate between M1 and M2, or a path whose edges alternate between M1 and M2, and whose end vertices are either M2, both M2 matched and N1 unmatched, or vice versa. If we look there at the path, then let's say your blue matching is M1. Right, so that's, let's call that M1, and your red matching is M2. Okay, so that's M2. Now, if you look at if it alternates, it either starts with blue or red. So if it starts with blue, again, you're going to have the alternation there. So you're going to have that, you're going to have that. Then you're going to have that eventually that's going to come in there, and it's going to happen here that you end up with a blue edge at the end. So again, these two blue edges are M1 matched, and they M1 matched, and in that case they are M2 unmatched. So if you look at any of the remaining edges, none of them is going to be a red edge, and on this side as well. Or you could have alternatively have that scenario there where the end vertices are M2 matched, and again they are M1 unmatched. So none of the edges here is going to be a blue edge. All right, so this is what we need to go and prove. We need to go and this is what the statement of the theorem is all about, and we need to go and just prove this. Okay, so before we look at the proof, here's just again another example of how this proof works, or how this theorem works. If you go and look at that sketch there, right, so there's your graph, and what we're going to do is we're going to take two matchings, a blue and a red matching. Let's look at M1. M1 is going to be the blue matching. So this is matching here, there, and there. So that's M1. Right, and then we've got M2, which is this matching here. So note that the red edges are all independent. They don't have any shared vertices. Right, so there's my there are my two matchings. Now let's look at the subgraph induced by the red edges and the blue edges. So we take the spanning subgraph by taking the edges from M2, and from the set of edges in M2 we remove all the M1 edges, and vice versa. We go to M1, and from that set we remove all the M2 edges, and then we throw the resulting edges together. Now if you look at M2, M2 doesn't have any edges in common with M1, and M1 doesn't have any edges in common with M2. So throwing the red and the blue edges together and looking at the resulting graph will give the following. Right, so we take the two graphs and we form the spanning subgraph with that edge set that I described. And we do that by, you can superimpose it like that to illustrate it. Okay. Right, so there we've got the graph, and then what we do is we remove all the other edges that are not any of the matching edges. Alright, so that what we're going to do there is delete the black edges. And we are going to delete that. And then also that. Okay, now what are we seeing here? We're seeing we're seeing a graph with two components. Now look at the one component, right? The one component is a path that alternates between M1 and M2. The two end vertices are, what are they? If you go back to your coloring, M1. They are M1 matched and they are M2 unmatched, right? And the other component, which is that component there, is a cycle. It's a cycle where the edges alternate between M1 and M2. It's basically, it's this property here, okay, and that property there that's satisfied in that particular example. Okay, so let's go ahead and prove it. So let's just take any component of this graph we constructed, H. Call it H1. Now, the maximum degree of H is at most 2. Now, why is that? Remember, in our example, we had the two matchings. We had a blue matching and a red matching, and all the other edges were colored black, right? The black ones, we deleted them at the end. So now, why is the maximum degree of this new graph H at most 2? Well, if you look at, if it is matched, M1, at least M1 or M2, if it has, say, if it's M2 matched, then it can't be M2 matched again, because then this will not be a matching. Remember, matching edges cannot share vertices. So it cannot be M1, it cannot be M2 matched twice, right? So the only other alternative is it's either M2 matched once and all the other edges are black, right? That can happen. Or it could possibly again be M1 matched, but then it can't be M1 matched twice again by the same argument. So that that can definitely not happen there. So it's either M1 matched exactly once, or it is M1 matched, or it's M2 matched exactly once, or it is M1 and M2 matched both exactly once. So the maximum degree of this graph cannot exceed 2. Now the implication of this is that this component is either an isolated vertex, or it is a path or a cycle. Right. Now, if this component H1 is a cycle, then obviously each vertex is incident with an edge in M1 and an edge in M2. By the same explanation that I've given previously, you cannot have a vertex incident with 2 red edges or a vertex incident with 2 blue edges. So you must have that alternation. So the edges of H1 must alternate between M1 and M2, and so H1 must be an even cycle. What happens if H1 is a path? If H1 is a path, then each n vertex is incident with exactly one edge. Either it is M1 matched and M2 unmatched, or vice versa. Okay, so that is pretty straightforward. Now, this brings us to the following idea. If M1 and M2 are matchings, where the one matching's cardinality is larger than the other one, then H as above has a component with more edges in M2 than in M1. Now remember, because the previous theorem states that you can either get each component is an isolated vertex or a alternating cycle or an alternating path. So the alternating cycles, they're always going to have just as many M1 edges as M2 edges. The isolated vertices, they're not going to have any M1 or M2 edges. So the only remaining components are path components. Now, if one looks at these path components, then if you have these path components, then remember your number of M2 edges is bigger than your number of M1 edges. Now, if each one of these paths has a situation where the number of M1 edges is bigger than or equal to the number of M2 edges, then you're going to get a contradiction with the fact that the cardinality of M2 is bigger than the cardinality of M1. So at least one of these paths must have more M2 M2 edges than M1 edges. So take a path that's got more M2 edges than M1 edges, and therefore the end vertices must be M2 matched and M1 unmatched. Right, so there we've got the illustration there. There we've got the blue M1 and the purple M2. M2 must have more, M2 has got more edges than M1, and if we look at this particular component, it must have more M2 edges than M1 edges, and therefore the end vertices are M2 matched and M1 unmatched. Now, if we drop M2, if M1 is not maximum, then G has a path whose end vertices are M1 unmatched and whose edges alternately are not in M1 and not in M1 and in M1. Right, so there's an interesting consequence of this, which we'll just investigate later. Now, this brings us to the definition of an M alternating path. So an M alternating path of G is a path whose edges alternately belong to M and not to M. Now, again, this previous example here was an example where the edges alternated between being in M1 and not being in M1. Also, an M augmenting path is an M alternating path whose end vertices are M unmatched. Okay, and again, this is an example of an M augmenting path because the end vertices of this path are M unmatched. Now, a quick observation. An M augmenting path P yields a bigger matching. It yields a bigger matching, so let's construct the following matching. So we'll go back to our previous example and we will construct a new matching. We'll take the augmenting path, we'll take our matching M, and we will basically we'll take the matching M, and from that we will remove all the edges on the path P, and then we will take the union of that with the edges of P without the edges that I have my matching, the edges that I have my matching on, or my coloring on. Okay, so what I'm going to do is I'm going to just illustrate this with our previous example. So we're going to take an M augmenting path, and then we're going to construct the following matching. Back to our previous example, let M now be this matching, and the matching is composed of the red edges, and then what we did was we superimposed it like that, and we deleted the irrelevant edges. And the irrelevant edges were all the ones that, well, the blue ones are now just, we sort of treat them still like black edges, but we're not going to delete them, otherwise it's not going to be a good illustration. So remember, we got this this path in this cycle. Now, if you go and investigate this, that is a path P. Now, this path is it's an M augmenting path. The definition of an M augmenting path, it alternates with regards to M, and its n vertices are M unmatched. So if you look at the n vertices of this path P, there are no red edges incident there, so it is M unmatched. So that's an M augmenting path. So what we want to do now is we want to construct a new matching. This new matching is the matching M prime, and it's composed of the edges. I take my matching M, which is the red edges, and from that I take out all the edges that are on the path. Take the union of that with all the edges on the path without M. Right, let's look at this set first. M, which is the set of all of the red edges, minus all the red edges on the path P. So which are those edges? Right, so it's pretty much all the remaining red edges. So it is going to be that edge, that edge, that edge. Okay, so let's we form our new matching M prime. So we're going to call that a purple matching. Okay, so we're going to do that, and we are going to, there is my new matching. Okay. Okay, so that is pretty much that set taken care of there. And now what we're going to do is we look at, so M prime is going to be the set of purple edges. So let's look at that set there. It's the edges of the path that I'm going to take, and I'm going to subtract from that the number of red edges. So you're basically going to subtract that edge. You're going to subtract that edge. And now what you're going to do is the remaining edges of the path, you're going to add that to my purple set. And so therefore what the situation there is now you are adding that to my purple set. Okay, so that is now a new matching, and that's the matching M prime. Now, how many edges does the matching M prime have in this particular example? Well, we can count that as 1, 2, 3, 4, 5, 6. Now, if we go back to our original matching M, our M matching has 1, 2, 3, 4, 5 edges. So now we've created an even bigger matching. So remember, M is obviously not a maximum. It's not a maximum matching, because we've managed to construct an even bigger matching of purple edges. And in the purple edges we have 6 edges, and in the red set we've only got 5 edges. So it seems this is quite an interesting situation here. It seems that if you have an M augmenting path in one of your components, then you can construct an even larger matching, and that is going to bring us to the following result. And it's about a matching M is maximum if and only if G contains no M augmenting path. So this is a nice little characterization or a necessary and sufficient condition for M for a matching to be maximum matching. So we'll prove this by using this idea that I've just illustrated, that if you have such an augmenting path, you can construct a particular matching that is larger than M. So let's assume M is maximum. And let's suppose to the contrary that there is an M augmenting path P, Well, then as above, we can find a matching with more edges, which is a contradiction. And what is that matching? That matching is the one that we described here, where you take a new matching formed by taking you take the matching M, and from that you subtract all the M edges that you have that lie on that augmenting path, and the remaining M edges you all color them the same color, a new color, and then you together with that you throw in all the edges of the path, with exception of the M edges that lie on the path, and those remaining edges on the path you color them with your new matching color, and so you'll construct a larger matching. Right, and the reverse is if G contains no M augmenting, well, let's assume it contains no augmenting path, and suppose that M is not maximum. So you can find another matching that's got more that's got strictly more edges than M does. And then let H be a spanning subgraph of G whose edge set is pretty much the edge set described there. Then this graph H is going, it's going to have a non-trivial component P that is a path whose n vertices are M unmatched. Now remember, where do they get that from? Again, they get it from this little explanation we gave here, where if you have this little situation here, you are going to get a path that's going to it's going to have more of your larger matchings edges than your smaller matchings edges, and then you're going to have you're going to have such an alternating path. Okay, and again, P is going to be an M augmenting path, which is a contradiction. Okay, so it takes those two little separate explanations together, and it throws it into a nice little characterization theorem. Okay, before we continue, just some notational issues. For bipartite graphs, we will bipartition these graphs into vertex sets or partite sets U and W respectively. And if M is a matching and it matches vertices in U, the vertices in U to a subset of W, then we will say that M matches the set U1 up until UK to the set W1 up until WK. So as an example here you see the edges, the blue edges are the edges of a matching, and the matching matches U to the set of vertices in U to these to a subset of vertices in W. Just an interesting observation. If there exists a matching M matching all of U to a subset of W, then every vertex of U has a matching partner in W. So a direct consequence of this is that the cardinality of S is at most the cardinality of NS for all subsets S in U, where N of S is just the neighborhood set of S. Now what the neighborhood set of S is, you take every vertex in S, you look at its open neighborhood, and basically you take the union over all vertices in S. So that is the neighborhood of S. And that's also known as Hall's condition. Okay, so it would probably be nice to just illustrate this. So if we look at our two sets U and W, and let's say there's a matching that matches every vertex in U to a subset of W. So let's say we have this matching here. Okay, so there's my matching. Now, if we look at a subset of U, right, so let's take our subset of U there. That is going to be S. And now we need basically to keep this in mind here, this condition we talked about. So if you look at the cardinality of S, I mean, you can clearly see that for every member in S, there's a member in W, okay, which you're going to count. Now, if you're going to count the neighborhood of S, you are pretty much going to count. You're going to count those vertices, okay, which is already the same cardinality as the vertices there. And then you're also going to possibly count way more. You're going to count way more vertices if you take the whole neighborhood set of S into account, because you could possibly count. You could possibly count way more vertices, right? So I mean, it's pretty intuitively clear that if for any selected subset S of U, you're always going to have this relationship here, that the neighborhood set S is going to be larger than, or at least the cardinality of S. And it's simply because you're going to count in the neighborhood of the neighborhood set of S. You're going to count at least these matching. You're going to count. You're going to count just as many vertices as you have there, at least, by counting the matching partners. Okay, so basically, this brings us to Hall's theorem. And Hall's theorem states that if G is a bipartite graph with bipartition U and W, then U can be matched to a subset of W if and only if this Hall's condition is satisfied. So we can take the vertices in U and match them to a subset of vertices in W if and only if. So this is a characterization, sufficient and necessary condition for me being able to match the set U to a subset of vertices in W. Now, to prove from left to right, we observe we look at the above observation, and that is if we can match U to a subset of W, then obviously Hall's condition is going to be satisfied by the explanation that I've given. So by counting the matching partners of the vertices in S, those matching partners are obviously going to be counted in the neighborhood set of S as well. So the cardinality of the neighborhood set of S is at least going to be just as big as the cardinality of S. All we need to do is we need to prove the reverse. So we are going to assume that G satisfies Hall's condition, but unfortunately there exists no matching that matches all of U to a subset of W, and then we're going to use that to get contradiction. So how we're going to do this is, let's choose M to be a maximum matching, and I want you to keep in mind everything we've done on matchings up until now. Right, so then there exists a vertex U in capital U that is going to be unmatched by M. And that is because, remember, we assume to the contrary that no matching matches all of U to a subset of W. So there's going to be at least one vertex in U that is unmatched. So now what we're going to do is we're going to define a special subset S of U, and we're going to define it as follows. So S is the set of all vertices in G such that there exists an M alternating path from U to V. Okay, so having defined that set, we look at U1 being the intersection between the defined set S and the partite set U, and let W1 be the intersection between the set S and the partite set W. Now again, another definition, for every X in S, we let P subscript X denote the M alternating path running from U to X, and note that Px starts from U and it goes from U1 to W1 down on a non-M edge. Then also from W1 to U1 with an up edge or an M edge. So it's alternating going down. It goes on a non-M edge, and going up it goes on an M edge. Alright, so having said that, what we claim now is every vertex in the union between U1 and W1 is M matched. U1 union W1 without U. Okay, so it's basically all these vertices that we're talking about. Okay, so here's our sketch, and the blue edges denote the edges from my matching. Now, let's see what happens if the vertex X, where, remember, we take X to be from the vertex set U1 union W1 minus U. Okay. Now, what happens if X lies in U1? Is X is it M matched or not? Now, remember the definition of the set S. There exists an M alternating path between U and X. So the M alternating path starts there, goes there hypothetically, then it goes up, then it goes down again. Then it goes up on a blue edge, goes down, and then to get to X again, it has to go up on a blue edge. So obviously the vertex X is M matched, and the matching edge we're talking in this particular case is that edge there. Right, now hypothetically, let's say X is a vertex in W1. Right, then, so we go down again on a non-M edge, then we go up again there with that blue edge, then we go down, we go up again on a blue edge, then we go down again, then we go up again on a blue edge, and then we go down to X. Now the question is X M matched or not? Well, in that particular case it is, but what happens if we have a situation like that? If X is not M matched, what is it going to mean? It means it is only going to be incident with non-M edges. And what is the problem if this happens? The problem with this is then that this path that we've basically highlighted here is what kind of a path? It is an M alternating path. Now remember, M is a maximum matching, and we already said that a matching is maximum if and only if there are no M alternating paths. Now remember what an M alternating path is. It's a path that alternates between non-M edges and M edges, and the N vertices are M unmatched. And here in this case what would happen is these edges are the N vertices are going to be M unmatched, because that vertex is not incident with the blue edge, and that vertex is also not incident with the blue edge. So that can't happen, right? So basically what we need to happen here is that there has to be somewhere a blue edge that is incident with X. So therefore X is definitely M matched. Okay, so that is what they say here. Everything I've said up until now is pretty much talked about here. Okay, so every vertex X in U1 union W1 without U is definitely M matched. Okay, so now from star, what does star imply? Now going back to my sketch there, U1 again is all the vertices in S where there exists an M alternating path between U and that vertex, and we know what W1 looks like. Now look at the cardinality of W1 with respect to U1. So let's count the number of vertices in W1. So for every vertex in W1 is matched to via blue edge to a vertex in U1. Right, so what's the implication of that? If you then look at the cardinalities, you're going to see that the cardinality of W1 is pretty much going to be the cardinality of U1 minus 1. And we're subtracting it because of that vertex there. So we're only counting these edges here. Okay, so the cardinality of W1 is exactly equal to the cardinality of U1 minus 1. Right, so we have that little relationship there. Now what we just claim is the following. We claim that the neighborhood, the open neighborhood set of U1 is actually contained in W1. Right, so let's assume to the contrary that it isn't. Let's say there's a vertex in the open neighborhood of U1. Let's say there's a vertex in that set that is not in the set W1. Right, so there's a vertex Y in the open neighborhood set of U1. Okay, and this Y is not. It is not in W1. Okay, so let's take the what we're going to do now is we're going to just illustrate it with the following. So what happens here is let's say my vertex Y is that vertex there. Okay, now firstly you cannot have obviously a blue edge running from X to Y, and remember Y is in the open neighborhood of U1. So that cannot be a blue edge. The only edge you can have there is basically a black edge. But what is the problem then? The problem again is that you can find this alternating path between U, right, that eventually gets to X, and it goes down to Y. Now, what is the problem with this? If we look at this path here, this is an M alternating path. It runs like that. And the problem with that is that, remember we said, what is the definition of the set S? The set S is all x or all vertices in W and U, such that there exists an alternating path between U and that particular vertex. So there exists an alternating path, M alternating path between U and Y. And the problem with that is then that we will have that the vertex Y will be in the set S. And that will imply that Y will be within W1, which is a contradiction, because here we said it isn't. Basically, our original assumption that there's a vertex in the open neighborhood of U1, but it cannot lie in W1, was incorrect. So it follows immediately then that we have that this set here is definitely contained within that set there. Okay, and that is basically everything that they talk about there that I've just explained. So immediately now, we have that the open neighborhood of U1, the cardinality is at most the cardinality of W1, because we showed those two sets are contained in one another. And W1 we said is, is at most U1 minus 1. And therefore this is going to imply that Hall's condition is contradicted. Hall's condition